everyone for coming to talk today about cathodoluminescent spectroscopy and imaging. So I'll talk a little about some basics and then quite a few examples of some stuff that we've done here at Ohio State, and then also some other literature examples of some kind of cool stuff that I've seen before. So other resources, Ashley just mentioned this, but you can attend the Beyond the Scope discussion series. We've been having them every Wednesday so far for the last few months. There's the link there. You can find the old ones if you want to catch up on any of those old topics. We're mostly working remotely still. So if you want to schedule any meetings to consult about any of the techniques, reach out to any of the instrument managers. For SEM, it's either myself or Stephen Buna. We are open on a kind of limited basis right now and are actually doing some experiments in labs. So you can reach out to us and we can try and see how to get that kind of stuff started as well. Or if you're working from home, there's a lot of data analysis resources we have as well. So before I get started with my actual talk, I want to give you a background if you don't know me too well. I did my undergraduate work in chemistry at New Mexico Tech. I focused on looking at kind of organic synthesis research. So I spent a lot of time in the wet lab there. Really enjoyed that. I've also loved playing around with building things, all that kind of stuff. So that kind of led me to what I did in my grad work at Penn State, where I kind of shifted over. I looked at optical properties of atmospheric aerosol particles. And with that, atmospheric aerosol particles, it was mainly building cavity reading down spectrometer system. And then also that led to quite a bit of imaging in the electron microscopes. That kind of brought me into that interest. Then I worked for a year at the Penn State Materials Characterization Lab, managing some of the SEM and FIB instruments before I moved on and did a postdoc position at EMSL at Pacific Northwest National Lab, where I kind of combined everything I've really enjoyed, doing some in situ microscopy, electron microscopy, as well as X-ray microscopy of atmospheric aerosol particles we collected from all over the world. And then doing that research brought me here to be a senior research associate in charge of some of the SEMs. And I kind of focus on doing advanced techniques and a lot of in situ stuff. So that's main background. You want to get to know me a little more personally. What I like to do is spend a lot of time outdoors, so hiking. Most vacations I'll find disc golf courses in the area that I enjoy doing. And then when I'm not traveling, working on a lot of projects. So that's some walnut that we had milled from our backyard, drying stuff I can play around with that this winter since it's dry, or doing house projects. So if you saw last time, my shower is almost complete. I'm just waiting for a shower head from Kickstarter. So at CEMAS, there's a lot of different facilities available. So ranging from our high resolution Titan and Themis TEMs to doing high resolution cryo work as well in the Krios. We have a bunch of focused ion beam instruments, and then on the non-electron beam side, there's a HeliScan for 3D data acquisition, and then XRD. Today, what I'm going to focus on is a couple different capabilities that are available and useful in the SEMs with cathodoluminescence. So our Apreo 1 instrument has a retractable cathodoluminescence detector, and the Quattro has a full spectrum cathodoluminescence system where it can do a lot of cool stuff. So I want to just talk about the basics of what signals are going to be coming off your sample and what information you get from them. So in the SEM, you have an electron beam, usually ranging from about 10 eV up to 30 keV to start probing usually surface, or you can do transmission with it if you have a STEM detector, or if you're doing mainly transmission experiments with high resolution, you can go 60 to 300 keV in the TEM. So what you have is your electron beam coming down and hitting your sample. If you look at this diagram, it's a very nice one that's going to show the interaction volume of your different signals that are coming off your sample. So the most surface sensitive signal that's going to come off your sample is going to be very low energy OJ electrons. And that's a completely different topic to try and understand surface chemical composition. Then if you're doing any imaging in the SEM, you've done probably a lot of secondary electron imaging, which if you're at lower KVs, you're looking really at the surface of your sample. And then penetrating a little bit further into your sample, you'll get signal from backscattered electrons, which give you information based on the composition as well as some grain orientation information. And then one of the main characterization techniques that people use in the SEM, energy dispersive X-ray spectroscopy, has a fairly broad interaction volume as well, as you can see there. So you have to be aware of that spatial resolution. And then cathodoluminescence out of all of these signals will have the broadest distribution of any of these. But again, you can kind of control that penetration depth and spread with your KV of your microscope that you're using. So in addition to those, if you're doing a transmitted beam experiments in the TEM or STEM in the SEM, you can look at the scattered electrons or inelastic scattering with EELS spectroscopy as well in the TEM. So what I'm talking about today is cathodoluminescence, and it's a technique where the cathodoluminescence, cathode per art, is basically, you can think of it as the electrons being emitted from your sample or emitted from the microscope, hitting your sample and forming some kind of luminescence, which these luminescence have different lifetimes. So you can think of it as luminescence or phosphorescence if it has quite a long lifetime to it. But think of the signal generation through kind of the Bandgap theory, or if you go to organic molecules like HOMO-LUMO and molecular orbital theory. So you have basically your filled bands with different electrons up to a certain level. And then above that, there's going to be a gap before they can be free electrons moving in the conduction band. So in between those, there's a band gap. So as your electrons hit your sample, they'll move up to the conduction band and then relax in some kind of mechanism, usually a lot of different trap states that'll be indicative of different things from your sample. So this video I have down here is actually an SEM video I took last week, so nat cam photo, where you can see the beam rastering across a sample that's covered in phosphors. And you can see that it's actually emitting light as it goes across. So it looks really cool, and you're actually getting something from it and can do some calibrations from there. So there's a lot of different things that can be done with cathodoluminescence. So I'll talk about all of these as we go along. So you can do a lot of different imaging, so panchromatic, red, green, blue, monochromated, polarized, depending on what detectors you have available. We'll be able to show you how to do a lot of different spectroscopy as well in the instrument. So I'll show you examples of some depth resolved instruments and also hyperspectral imaging, along with, you can look at how long the lifetimes of these actually are. So general applications, it's basically everything. There's been a lot of work looking at semiconductors with this to look at band gaps and different impurities and dopants in your sample, along with, you can look at surface plasmon resonances of nanoparticles, because we can get really high resolution with our electron beam itself. It's a very mature field, looking at geological samples. And then kind of an understudied thing that I've found is either looking at organic compounds or also labeling and imaging for like cellular structures. So what you can easily compare this to is CRT television. So this diagram shows the basics of a CRT television. It works exactly like this. So you have your emission source. You can think of that as your electron beam coming out of your instrument. You actually have your cathode, anode, accelerating your electrons down, focusing your electrons, and then deflection coil. So it's basically a really low resolution SEM there, and deflects the beam onto a fluorescent screen. And that fluorescent screen will have different kinds of phosphors on it, red, green, blue, to create your image. So in this case, this image, I'll show a couple of these in the next few slides. Stephen Boonett actually took these images. He found a old television and took it apart and was able to do imaging. So we have some samples, so it's pretty cool. But we can actually image if they're going to be red, green, blue phosphors. Or in this case, from this paper, they looked at the phosphors and understood what the actual emission profiles were from each of them. So I want to focus first on the insertable kinds of devices. There's a few of those out here. What we have on our Apreo instrument is one that comes with the instrument, made by Thermo Fisher. And it's basically just a retractable backscatter detector that gets inserted over your sample. So it's really nice. You don't have to do any kinds of alignments. It's sensitive between 350 to 900 nanometers. The one limit on it is you only can use it up to about 10 kV because it is a diode detector and those have enough energy to pass through the mask. But it's really fast for any kind of panchromatic or red, green, blue imaging. So if you look here, this is a basic ETD image. You can see all your particles. You don't have much information about the phosphors, but depending how you actually use the detector, you could use, so in this case, we're just using the red part of the detector. You can see down here, it's just gonna light up your red phosphors. You can use it for green, so you're looking at your green phosphors. You can just use the blue segment and your blue phosphors up near the top there. Or what they call true color, you can actually mix that all together and do some nice, basically color imaging of your sample and correlate those to it. There's also panchromatic imaging, which has basically unfiltered and it has spots all around the detector that can be used. And you can combine any of these to get as much signal as you want out of your sample. So since we were talking about the phosphors, we had these nice images that show a couple of different effects that you want to think about when you're doing any of this kind of imaging. So even in any kind of imaging in the SEM, you'll see this. But as you scan your electron beam across, you'll be getting signal from next to it. So in this case, you can see we're hitting the blue phosphor with the electron beam here, but you get a lot of secondary emission that's going to be hitting your red phosphor, and you're going to be getting emission from that, basically creating a red glow on the phosphors adjacent to it. So you just want to be aware of that. You'll even see that kind of effect with any kind of secondary electron emission as well, though it's not usually as pronounced as this. And also, as I mentioned before, each transition has a finite lifetime to it. So if you're looking at this image, it's nice, it doesn't streak at all. It was probably about 30 or so microsecond dwell time at high pixel counts. So if you try and go at really high scan speeds, even if you have enough signal, the phosphors are going to emit for a long amount of lifetime and you'll end up with streaking. So you can either bring your dwell time very far down, so it'll take a long time at each pixel, so hopefully about 3 pixels down, you won't be getting emission from the ones before it, or you can just increase your number of pixels as well. It'll take about the same amount of time. So the first example that I want to talk about that was done on the system was a shale sample from Julia Sheets and Susan Welch, the Coal Research Group in Earth Sciences. And they're interested in the sample. We were kind of just seeing what we could see with it, and then I'll show you some comparisons with some of their other data. But this is one of the favorite crystals that they have in there, and they understand quite a bit. It's an apatite crystal, and what you can see is a lot of different zoning within the crystal itself. So you can see that it's going to be brighter in the center along these axes, and then a little bit darker here, and then you don't really get much fluorescence outside of this single grain. except for some other smaller grains there. So you can kind of start to understand what's going on there. And it's a very high resolution technique. So these images are fairly quick to take at high resolution. So if you zoom in on this corner, you can see there's actually quite a bit of differences in here. So it's either going to be concentration of activator elements or possibly even different activator elements depending on what it was actually exposed to during formation of this mineral. And like I said, they've done a lot of work on this before, so there's some cool comparisons that we can do from their work with their SEM at SEMCAL. So if you just looked at this normally, you would assume for backscatter imaging, it's a fairly uniform crystal. Even if you're doing a EDS mapping from it, you can see that it's identified basically as apatite from its concentrations. You don't really get too much more information from its trace elements. But then as soon as you start to use like panchromatic CL imaging, then you can see there's definitely something else going on in this sample. It doesn't have a lot of specificity into what those actually are. You can do some literature and figure out possibly what it is. But they'd also done quite a bit of tough SIMS work at Oak Ridge National Lab. So you can see that actually the outside of this sample, so strontium, is going to be out here along some calcium, and that corresponds to their other mass here of some kind of strontium complex. And then on the inside, where you can see it's kind of brighter here, that corresponds to cerium. So you can get that information from other sources that correlate very well with cathodoluminescence imaging. So the second one I want to look at here was another geological samples that we were looking at. So this data is from David Young in Earth Sciences again. And what he's interested in looking at was going to be zircons. So zircons are going to be very often found in geological materials, and they can give you an idea of the geochronology of your sample. Zirconium oxide, it's not very soluble, so you're not having to worry about the solubility there, and it'll grow in different length scales. But it'll also tell you what's going on down the core. So as it heats up, it will melt, so you'll end up with other aging effects there. So you can look at them and use cathodoluminescence to see what zoning's happening there, get some idea of that, and then also use some kind of mass spectrometry. So in this case, David had used LIBS, and you can see the 30 micron holes that have been hit in each one, and then use the uranium lead to kind of do some dating of these materials as well. So it's really cool to use this as a complementary technique to a lot of other ones. Okay, so I want to go a little bit more into the Quattro and what's available on there, since it's a very complex system. I've talked a bit about everything that's available on it before, so I'm going to focus on our CL system. And how the signal is actually collected is going to be quite a bit different than how it is on the retractable backscatter. So retractable backscatter is the detector, whereas this, we're going to insert a parabolic mirror from the side. So this is where the mirror comes in. There's our sample. So this diagram, there's sample, we're about a millimeter or so away from the bottom of the mirror. And as your electron beam passes through a hole, you'll have your signal coming off and it'll get passed to the spectrometer. So it's really nice. You can get a lot of signal from your sample from this, since you have a large collection angle. It's usable at any kV, so that's one advantage. You can go up to 30 kV and understand it for some more depth resolved imaging or anything. But it does have a smaller effective imaging area because you do have that pinhole that you're going through, along with some focusing effects, trying to get as much signal into the spectrometer as possible. But in it, we can do a lot of different things that I mentioned before. So I just want to go over how we can do all that stuff. It gets to be a little bit cumbersome and busy here, but so we have our spectrometer, our CL signal coming out, And so that's shown here. Again, all the light coming out of it. So it's passing through your retractable mirror. And you can use a switcher box and bump it over and hit the panchromatic detector. So if you do that, you can do panchromatic imaging with it. Slower than the Apreo one, but you can get more signal out of it if you need it. Or we have polarizing filters, so we can do those kinds of experiments as well. Or we can throw in red, green, blue filter here. And again, it's just imaging one color at a time, but it's a nice way to start looking at your sample if you're going to be doing some more complex analysis with the system. Next thing you can do is bypass that system and go directly to the imaging spectrometer itself. We have 3 different diffraction gratings. I'll disperse your sample and either go to the CCD detector or down to the in-gas detector if you're trying to look at IR. So the detector response I'll also show here, but basically with the CCD, you can use anything from about 200 to 1,000 nanometers. Is about where it's going to be useful at, whereas the in-gas detector will pick up from there, and it's a little bit better from 1,000 up to 2,200 nanometers. And a system with all the ports on it, it's actually very customizable as well, so that's why we ended up getting this system compared to some of the other systems. So if we want to switch out detectors, it is doable. So if people have interest in doing any kind of other work, we can always talk about that and see what can happen. So I just wanted to go back to the phosphors. So if you remember, super bright from the initial scan. And what we can see here is if we look at secondary, backscatter, or panchromatic, you see there's kind of one bright one there. You do your red, green, blue imaging, you can see there's actually some of these phosphors that are supposed to be fully green. There's a few that are actually more blue. So that's where we would stop with the Apreo system. But here we can do spectroscopy on it as well. So here's a graph of what that looks like. So most of these green phosphors are gonna be around 550 nanometers or so. And then if you look at the spectrum of this blue phosphor, it's gonna be around 450. So you can start to get some information from that. But if you want to start getting any other information from it, what I did here is I looked at the same phosphors as well with energy dispersive X-ray spectroscopy. And what I saw is basically with this blue phosphor, there might be a little bit more copper nickel. And if you look at this, you'll wonder why there's shifts and a huge background there. So this is something you need to worry about if you're trying to look at anything that's going to be fluorescing quite a bit, doing EDS work on it. So you have all that signal that's still going to be hitting your detector. It's going to be collected as light. And so the more intense it is, will shift your peaks. So in this case, you can see the sulfur peak got shifted as there's more intensity. Or you'll end up with a continuous background as well. So one sample that's kind of cool on the geology aspect of this is a sphalerite mineral, where we had some of these grains. It's just a zinc sulfide mineral. And what you can see with panchromatic imaging is there's a fairly dark area here where we don't get a lot of signal from it, get a lot more signal here and then less signal here. So gives you some idea what's going on, but if you pick, so black is going to be this darker area, green's actually the center area, and blue is going to be there. So if you look at that center part, we did a hyperspectral map there. And if you pick just a monochromated imaging at 390 nanometers, you can see that we get high fluorescence up there, which then you could correlate that back to something else if you know what activator elements are there, or this single peak at about 500 nanometers. You can see it's really bright in the center, but there's also other zones right near the outside of this that show up. So that gives you actually more information than I originally realized when I took the image. And then at the brightest peak here, it's going to correspond to at 790 nanometers. So it's really nice being able to understand that, gain some spectra from it that we can go back and characterize further. So switching gears a little bit, I'm going to talk a little bit about more things in material science. This is some work that was been done by Ari Bloomer in the Grassman Research Group in Material Science. What they do is looking at materials where they're growing films on gallium nitride, I believe in this case. And what they're looking at is wondering how these kind of dislocations and defects affect the properties of the sample. So what they can do first is some electron channeling contrast imaging. So ECI work here. If you're interested in learning more about ECI, Tyler's going to be giving a talk on that in a few weeks. So I'm not going to talk too much about here, but if you get the right diffraction conditions, you can start to see these dislocations. And from that, as soon as you switch over and do CL on it, you can see kind of what's actually active from there. So you'll get more or less signal where those dislocations are happening. And if you want to even take this further, they did quite a bit of hyperspectral mapping of the samples as well. So this is, again, an identical area of it. And at each one of those pixels, a spectrum is taken. So this one you can see, if you're in from about 660 to 712, it'll be more blue, whereas if it has higher intensity in the 712 to 750 nanometer range, then it's going to be more red. So you can start to understand what domains and everything are happening within your sample itself. And the second sample that I was looking at with this, so this data is from Reza Harim and the Hongming Zhao group in ECE. And again, they're growing films. So they're growing zinc germanium nitride on gallium nitride templates. And if you look at these, they're fairly flat. There's not a whole lot to see on them, but we can start doing some depth profiling with CL since we can change our KV. And what we can see with that is if you have really low KV, so this red peak here, we start to see peaks around 625 or so. And so those are going to be correlated to some of the defects in the film. So that's really interesting to see that. Then you could do some other work if you know your film thickness and everything to know how far you're actually penetrating into your sample. So you have to do some modeling to actually characterize it a bit further. But then as you increase your KV, so at 5 or 10 KV here, you can see the peaks start to change. So this is peaks more defects in your gallium nitride layer. And that peak increases as you're gain more electrons down to your gallium nitride layer. And then as soon as you're going 30 kV, you're penetrating mostly into the bulks. You'll get a lot of signal from the bulk, and you're going to be getting primarily that signal. And then also you can get that near a band edge peak from the bulk sample since you're getting so much signal from it. And then the last two examples that I'm going to talk about are going to be from literature sources that I found that I think are very interesting. So this first one is going to be a cross-section of a pharmaceutical tablet. So this pharmaceutical tablet, if you look at it with secondary electron imaging with a cleaved surface, you see a rough surface. You can't really characterize a whole lot from it. And since there's a lot of organics in there, it's going to be very beam sensitive. So these experiments can be difficult to do. But what's nice about these samples is they have aromatic regions in them. So if you have these, then the homoluma is going to be close enough where you're going to be able to get some luminescence from them. And so this ibuprofen, you get a decent luminescence at about 510 nanometers. So if you map that out across here, you can see the distribution of your ibuprofen. Or this codeine phosphate, it has emission at about 350 nanometers. So you can map that and you'll see its distribution as well. And then if those are your only two components and the rest is binder, you know that the rest can be more or less binder within your sample. So you can get a lot of information from that Beforehand, you could do spectroscopy on bulk powders to actually narrow down what wavelength ranges you'd be interested in there. So I thought that was really cool as a different application than has often been used for CL. And second is a more recent development that people have been trying out. So what was done in this paper is they synthesized a bunch of nanoparticles and changed the different kinds of dopants in them with a lot of different lanthanide dopants in them. And what you can see here, so this is a secondary electron image, and you can pick out basically the location of the particles. If you need to see the actual size, you'd want to go to TEM for that. But on a really high resolution scale, you can know where these particles are actually located. So if you can then put some kind of binder on them so that they will bind with a protein, then if you put in a cell, it's kind of cellular matrix, then it could actually bind with those proteins and you could image where those nanoparticles ended up. And the really cool thing that they showed is here you get plenty of signal from these particles that they made, but then also depending on your dopant in them, you get very different spectrum. So if you do spectrum imaging of these and you have different tagged nanoparticles with different dopants in them, you could actually look at a complete cell possibly and understand where they congregate into a few different areas based on choosing the monochromated imaging in those. So it's a really cool application that I'd love to try at some point, but we can definitely do some high resolution work with this technique. So that's what I have for that. And I just want to mention the takeaway points again. So with cathodoluminescence, you can do a lot of imaging within your sample. So panchromatic and red, green, blue imaging, or you can go on and do a spectroscopy and even hyperspectral imaging to get that spatially resolved spectroscopy. And I didn't talk about any of the work here, but it can be also correlated with in situ experiments. So it's compatible with heating, cooling stages. Heating, you might get a lot of IR depending on where you're at there, but cooling your sample, you can reduce beam damage and then also see how things shift as well. And definitely it's easy to use it with EDS, EBSD to correlate within the same instruments. And as I kind of showed, there's just a huge range of materials and applications that can be used. And it's very used in a couple applications, but it's always fun to see what new ideas people have for it.